welcome to the video on the intermediate value theorem. So in a casual sense, the intermediate value theorem, which I'm going to abbreviate as IVT, says that a continuous function, so a continuous function cannot skip, can't just skip values, okay? So values being values on the f of x or the y-axis, okay? So it just can't skip values randomly. And a converse to the theorem is that a discontinuous function, so one that is not continuous, a discontinuous function can skip values on an interval values. So what I mean by this is that the intermediate value theorem says, let's say you have a continuous function, right? So something like that. Okay, something like that. So on this interval, from here to here, so here's the first value that we see on our interval, and then here's the last value, so that's about here, okay? So that means that on this entire interval, on this entire x interval, here's our y, x and y, so on our entire x interval, it ranges from values of f of x being the first value here and f of x being the second value there. So it has to hit every single point on this interval on the y-axis. See that? So it doesn't say anything about going outside of that range, but it does say, because it says intermediate, so that means between, in the middle, between. So all it is concerned with is what is between those two, the beginning value and the ending value. Whereas a discontinuous function, so this is a continuous one, right? So that's continuous f of x. Whereas a discontinuous one would look something like this, okay? And let's say it has a hole here for some reason, right? And then it goes down there, okay? So in this case, here's our start and here's our end of our interval on x. So from here to here, it should have a continuous, well, I should not skip values, but we have this discontinuity here, right, at this point. So let's see what happens. So our starting f of x value is up here. Okay, so that's our starting f of x, and our ending f of x value, or our y value, is down here. All right, so this is our ending one. So technically, if this were a continuous function, it should, according to the intermediate value theorem, on this interval on x, the one down here, so on this interval, it should hit every value on the y-axis, okay, in between our start and our end point of f of x. But we have this discontinuity right here, that glaring discontinuity. So that means that this value here is not hit. So that means it is skipped, all right? So this is an example of a discontinuous function, which doesn't disprove the intermediate value theorem, but it is a converse of it, okay? So an opposite example. All right. So in a formal way, so this is the formal definition, so formally, the intermediate value theorem says the following. Okay, so if f of x, so if our function is continuous, so we're assuming right away that it's continuous, so continuous, on a closed, and closed meaning includes the endpoints, closed interval, and they usually just reference it as AB. So we're going to use square brackets because it includes the endpoints, okay? And if f of a, so the function evaluated at a, is not the exact same as the function evaluated at b, comma, then we have, so here's our conclusion from the theorem, for every value, m, for every value m, and value meaning the y value, the f of x value, not the x one, but the f of x, between f of a and f of b, okay, there exists, sorry if it's kind of long, but just going to copy it down and then I'll go through and explain what I'm writing. So there exists at least one value C, so many letters, in AB, in open interval AB, so this is open interval does not include the endpoints, such that f of c, f of this x value is equal to m. Okay, so what do we mean? That's a lot of words there. So if f of x is continuous, so okay, we're setting it up as a continuous function, which means it cannot skip values, right? Okay, on a closed interval ab, so we're just basically studying it on one interval, and f of a does not equal f of b. So what we have, here I'll draw a little picture. So here's our x and here's our y axes, right? So let's say we have something like some function like that, okay? And here's our a on the x-axis, and here's our b. So that's an a on the x-axis, and there's the b. So this point here, this is level with f of a, okay? And this one up here, that height is at f of b on the y-axis. So this is our f of b, okay? So those are the values. Those are the endpoint values, right? So then it says, so that's our setup. F of a does not equal f of b, because if that were true, then they would be level, and that wouldn't really tell us anything. Anyways, so then for every value m between f of a and f of b, so now what that's saying is, like I've mentioned before, every value here on the y-axis, every value in between, so this is being represented as a collection of m's, just random y values, right? So everything in between, not including the endpoints, is our m. There exists at least one value c, so for any randomly chosen m, so I'll choose a point here, okay? So if we choose this y value m, and we draw a line straight across, we should find a point on the graph, okay? So here we hit a point, there, and then it says there exists at least one value c in the interval, or in the open interval ab. So that refers to some x, that basically means there is some x value in between AB, such that it makes it fulfills that point M. Okay, such that when you plug it in, you get that value M that you're looking for. Okay, so it's basically just saying, it's reinforcing that there are no discontinuities in the graph. And because we know that there are no discontinuities, because we're assuming that or maybe we're told that the function is continuous on this closed interval, then we can basically make these conclusions. Okay? Alright. So now, going a little bit more, not in detail, but what else can we do with the intermediate value theorem is we can prove the existence of zeros. Zeros. Okay, so this is actually pretty handy. So basically, a lot of times we can use the intermediate value theorem to prove the existence of zeros. To prove the existence of zeros. Okay, and what does this mean? So basically, zeros are when our f of x is equal to 0, when the y value is actually equal to 0. Okay, so how do we do this? So first of all, what we do is say that if by chance f of x is continuous, okay, if f of x is continuous on the closed interval a to b, this is our x interval, and if f of a and f of b are non-zero, are both non-zero, not equal to 0, and they furthermore have opposite signs, so that means one is positive and one is negative. It could be either one, opposite signs. Then f of x has to have, or has, a 0 on the on the open interval a to b. Okay, so pictorially, this is what that looks like. So let's say we have some graph. Okay, I'll just draw it kind of small down here. Let's see. Okay, so let's say here's our x, here's our y. So if we have something, here's point A on the x-axis, and here's B, right? So let's say f of a starts down here. Okay, so f of a is all the way down here. So f of a is negative, and f of b is positive, right? This y value is positive. And if we're told the function is continuous on this closed interval, then that means that at some point this graph is going to have to cross the x-axis. So here, it would cross, right? So it has to have a 0 because the f of a started off negative and the f of b is ending up positive. So at some point, it has to cross neutral, which is the x-axis at y equals 0. Okay? All right, so let's see one more example. We'll do the reverse way, just for more detail here. So let's say here's our a, here's our b, and this time f of a is positive. Okay, so here's our f of a value, that's positive value, and f of b, all the way down there, so f of b is a negative value. All right, and now we want to connect these, and we know that the function is continuous, so we can't have like an open dot there on the x-axis or anything like that, so it must cross at some point, and that point on this graph happens to be right there. Okay? Alright, so that's what it is conceptually. And now, in a more accurate sense, I'm going to introduce the bisection method.